Alright guys, in this section we're going to be discussing fundamental identities. If you recall from previous sections, we have talked about reciprocal identities, quotient identities, Pythagorean identities. And when we talk about identities, we're referring to an equation that has already been proven to be true. In this case, for these identities. We have also seen co-function identities and even and odd identities. And in this section, we will learn how to use the fundamental identities to evaluate trigonometric functions, to simplify trigonometric expressions, and moving forward, we'll also develop additional trigonometric identities and also ultimately solve trigonometric equations as well. Here we have an example of how we can use our fundamental identities to evaluate trigonometric functions. So we have tangent of x is equal to 1/3, and we're given the cosine of x is less than 0. In previous sections, we would have done this with right triangle trigonometry, but now we can use our identities to also come up with the remaining trigonometric functions. So restating here, tangent of x is equal to 1/3. By reciprocal identity, we know that cotangent of x is equal to 1 over tangent of x, which would be equal to 1 over 1/3, and that's equal to 3, or 3 over 1. So there we have it. And now we can use our Pythagorean identity, right, one of them, to find secant. So again, we were given tangent, right away we found cotangent, and now we can use our Pythagorean identity, 1 plus tangent square of x equal to secant square of x, to find what secant is. Substituting what tangent of x is, 1/3 square is equal to 1/9. So 1 plus 1/9 is equal to secant square of x. So then the left side would be equal to 10 over 9 is equal to secant square of x. Taking the square root on both sides, we're going to have the secant of x is equal to square root of 10 over 3. And remember, this is negative here because we're giving in the problem the cosine of x is less than 0. So since the tangent is positive and cosine is negative, this has to be on the second quadrant. So therefore, secant will also be negative, and that's why we added the negative there. So from here we have the cosine of x is equal to 1 over secant. And since we already figured out what secant is, we can just plug that in and find what cosine of x is. This is going to be equal to 1 over negative square root of 10 over 3. You see all of that is equal to negative 3 over square root of 10. And rationalizing it, we get negative 3 square root of 10 over 10. Now, so far we have tangent, cotangent, secant, and cosine. Now we have 2 more to go. We're going to use our quotient identity now, which says tangent of x is equal to sine of x over cosine of x. And since we already have tangent and we have cosine, we can solve for sine of x here. Sine of x is equal to tangent of x times cosine of x. And then substituting what we already have for tangent and cosine, we get 1/3 times negative 3 square root of 10 over 10. The 3's cancel out, and we get the sine of x is equal to negative square root of 10 over 10. Finally, the last trigonometric function is cosecant. Cosecant is 1 over sine, using our reciprocal identities. And since we just figured out what sine is, then that would be equal to 1 over negative square root of 10 over 10. So we end up with cosecant of x equal to negative 10 over square root of 10. And we can rationalize it again, and we're going to end up with negative square root of 10. Here's an example where we'll use the fundamental identities combined with some algebraic techniques to simplify the following trigonometric expression. We start by factoring cosecant of x, since they both have cosecant of x in common. We get cosecant of x times cosine square of x minus 1. And if you remember your Pythagorean identity, this looks very familiar, and it happens to be sine square of x. So if you're look at or recall your Pythagorean identity, sine squared plus cosine squared equal to 1. You can rearrange those terms any way you want to use them in your simplification here. So once you do that, we change cosecant to 1 over sine using our reciprocal identities, and notice how 1 sine of x cancels out from top and bottom, and the final answer is sine of x. Now here we have a few more examples where we're asked to factor each expression, and factoring is something that we're going to be doing a lot. We'll start with the first one here. 1 minus cosine squared of x. Remind us of the difference of squares, right? So 1 is the same thing as 1 squared minus cosine squared of x. And we know to factor this out is 1 minus cosine x times 1 plus cosine x. And that's it. We factored it. We're not necessarily simplifying here. We're just practicing our factoring techniques, okay? Now on the next problem, we have something that looks like a quadratic. So if you didn't identify the pattern, let me replace cosecant of x for a box here. And remember, that used to be our x or our variable in algebra, but it has that same quadratic form. So we're going to go ahead and factor this where we have a quadratic and cosecant. And factoring this quadratic-like expression, we get 2 cosecant of x minus 3 times cosecant of x minus 2. Again, you should be able to factor any trinomial from algebra because we're going to identify those patterns here. Now for the next one, notice how I don't have a quadratic on one of the trig functions. So this is where our fundamental identities come into play. So if we can change one of the terms so that we have all of it in terms of tangent or in terms of secant, then we could factor it like we did on the previous example. In this case, we're going to use our Pythagorean identity and look at secant squared of x is equal to 1 plus tangent squared of x. And replacing that, we'll change everything in terms of tangent. We combine the 1 with the 1 and give it the form of a quadratic, and then we have the problem quadratic in tangent. From there we can factor it into tangent x plus 2 times tangent of x plus 1. Here's another example where we're asked to simplify, and looking at our fundamental identities, we go ahead and change cosecant of x into 1 over sine of x using our reciprocal identity, minus cosine of x times change cotangent of x into cosine of x over sine of x using our quotient identity. From there we combine the cosines of x. Cosine of x times cosine of x is cosine squared. Notice how both expressions, both terms are being divided by sine of x, so we can put them under the same fraction. And notice how the top, the numerator, ends up being our Pythagorean identity again. And we get 1 minus cosine squared of x is equal to sine squared of x by Pythagorean identity. All that is being divided by sine of x. And then, of course, 1 sine of x gets simplified from top and bottom, leaving us with just sine of x. Here we have an example where we're going to have to perform an addition here of fractional expressions before we can simplify. So in order to add two fractions, we need to find the least common denominator and then figure out the numerator and simplify from there. So adding to these two fractions, we get the least common denominator is going to be the product of the two here. So 1 plus sine of x times 1 minus sine of x. And on top, we're going to get 1 minus sine of x plus 1 plus sine of x. Notice how the sine of x cancels out with the negative sine of x, leaving us with 1 plus 1 on top. Now, another way you can think about this is you can come up with equivalent fractions for these two fractional expressions in the following way. So again, this will be another way of adding these two fractions. We're trying to have the same denominator for both of them so that we can combine them easily. Once we have them together, we simplify the top. We just have a 2 over in the bottom. You distribute and get 1 minus sine squared of x. And the denominator should ring a bell. It looks a lot like our Pythagorean identity. And we can replace that with cosine squared of x. Now we can go a step further here and change cosine of x into secant, or 1 over cosine of x into secant x. And since this is a square, we'll end up with 2 secant squared of x. Here's another example where we're asked to rewrite this expression so that it's not in fractional form. So this is something that you'll do a lot in calculus. And one way of accomplishing this would be by using this conjugate ideas. Notice how you have 1 minus sine x on the bottom. And if I wanted to use an identity here, the bottom here, if we don't want this to look like a fraction, we really just need to take care of this denominator. So one way of doing that would be by multiplying by 1 plus sine of x on top and bottom, so that we don't change the expression. And notice that by doing that, we're going to, on the top, I'm going to leave it the same way, so we're not going to distribute, and you'll see why. And on the bottom denominator, I will distribute those two, and I'm going to get the difference of squares that we've been getting. And notice how that looks like my Pythagorean identity, and that was the whole purpose of multiplying by this specific expression. So on top, I still keep it the same. The bottom changes to cosine squared of x by my Pythagorean identity. And then now notice how I have cosine squared of x on top and bottom, so they cancel each other out, leaving me with 1 plus sine of x, which is not in a fractional form anymore. This next example involves trigonometric substitution, and this is a skill that would also be used in calculus. But here we have x equal to 3 sine of theta, and they're giving us theta to be in the first quadrant. They want us to write the square root of 9 minus x squared as a trigonometric function of theta. So all we have to do is substitute what x is and simplify from there. So we have the square root of 9 minus 3 sine theta squared is equal to 9 sine squared of theta. And notice how the radicand, the two terms there, have 9 in common, so we factor that 9 out, leaving us with a square root of 9 times 1 minus sine squared theta. And the whole point of this substitution is that we identified the Pythagorean identity there. We change that 1 minus sine squared theta to cosine squared theta. And notice how our expression inside the radical is a perfect square now, so that we can compute the square root. Square root of 9 cosine squared of theta is equal to 3 cosine theta. One last example involving logarithms. Here we're asked to rewrite this expression as a single logarithm and then simplify the result. So we're going to use our properties of logarithms here, where we have the sum of two logs can be represented as the log of the product of the two factors there. Natural log of absolute value of secant of x times sine of x. Now we can simplify the inside of the logarithm here, and changing secant to 1 over cosine using our reciprocal identities times sine of x, we get the natural log of sine x divided by cosine x. And if you recall our quotient identity, that is equal to natural log of the absolute value of tangent of x.